What's up, everyone? About 2.5 weeks ago, I made a video about doing partial fraction decomposition with 3 different methods. And in the last method, I used a very tricky thing and not commonly seen so that we can get the answer quickly. And I'm glad that there are some comments that ask me what that is and how does that help us to get the answer quickly, and also what is it related to, or how does it work. So today we're going to talk about what that is, or to be specific, it is a function, but what kind of function it is, and briefly explain what does, and briefly explain where it comes from and how it works, so that we can see why we will be able to get the answers quickly for partial fraction decomposition. So we'll first talk about the example 1, and then we will jump into the more complicated example, which is the second one. And if you have not checked out the video that I made before, please go find out first, so that you kind of see where this is approaching to. Okay, so first, let's talk about what this thing is. This is actually called the residue of the function when x is equal to whatever the number it is. So for instance, this one right here is a residue of the function, which is the expression on the left hand side, when x is equal to 2. And the word residue just really means the remainder or the leftover parts of whatever we're dealing with. In this case, it will be the expression on the left. So let's see. Let's talk about what it will give us first. And later on, we will just explain where it comes from and briefly talk about like how we build up and get this residue function. So for the application part, we will have the residue of the function when x is equal to 2. By its definition, will be taking the limit when x is approaching to 2 of, we're going to take this function f of x times whatever the denominator we have, which is x minus 2. And in fact, when we write this way, we always want to write x minus 2 into the first power, at least in this situation. And I'll explain when we have different power in general, okay? So let's see what we get. Since we have f of x is equal to this expression here, we can cancel out x minus 2 with the x minus 2 in the denominator. And again, that's what it really means by taking the residue, or the leftover, because we are now trying to take away something that we can't really do and see what else we can get. And at the same time, we can see that why we will have to take out x minus 2, because we're doing the limit when x is approaching to 2, giving us 0 over 0, and that's why we need to somehow want to get the x minus 2 term away. So we end up with 3x plus 5 over x plus 1 in this situation. So now we're going to substitute x by 2, or taking the limit, giving us 11 over 3. And that's how we get the residue, which is the coefficient of the x minus 2 to the negative first power term. Great. Then let's do one more example, which is now the second one. Residue of the function with respect to -1. So again, let's use the definition first. This is the same as taking the limit when x is approaching to this time. We have -1 here, so x is approaching to -1. And then we're going to multiply something with the original function f of x. What we're going to do is we're now going to multiply x minus whatever the number we have here. So we can see that this time it will be different from what we have in the first case, which is multiplying with x minus 2. This time we have to multiply with x minus -1, or equivalently x plus 1, so that we can cancel with the x plus 1 in the denominator. Then everything else will be non-zero, which will give us what's so-called the remainder or the residue. So we now get the product right here becomes 3x plus 5 over x minus 2. And if we simplify it, we get to -2/3. Cool. So where does this come from? Again, we said that it is actually from complex analysis, and complex analysis is just a study of functions in the complex world. But we can also think that functions that are in the real world can also be applied to the complex world. Again, real numbers are part of the complex numbers, and we just need to have some nice conditions so that we'll be able to use those ideas. And one of the big things in complex analysis is called the residue theory, which is actually bringing us the idea of residual functions. So it is actually very hard to explain in a short amount of time. So if lucky enough, I'll make another series of video, a series of video. So if lucky enough, I might just make a series of videos about complex analysis. And again, I'm not a professor. I'm just trying to explain with what I've learned in complex analysis and bring out those new ideas. Okay. Then what else I want to talk about? Right. The residue here. We just said that in the first example we have here, we always just multiply one copy of whatever the denominator is, so that we will be able to cancel out and get the remaining part, or the residue parts. And again, we can also think it like with the hand covering method. Because in this case, if we look at the expression on the right-hand side, which is the definition of the residue functions, we can see that all we need to do is to cover up wherever the parts that are in the new denominator in the partial fraction. And then we just need to substitute the x values that we're covering into the remaining part to give us the residue or the coefficient. What if the denominator is not linear anymore? What can we do? Or let's say if we have the second example, how are we going to change the setup of our residue, and how will it look like in general? We're going to discover a little bit more in the second example. All right. So here is the second example from the short. All right. Here is a second example from the old video. which this time has, of course, x minus 2 and also x plus 1 in our denominator still. But there's a little difference between the first example and the second example. In the first example, all the denominators will go up to the first power, meaning they're all linear. This time, however, we have a square in one of the terms, which is the x minus 2 term. So if we do the partial fraction, we know that we have to write in three parts: x minus 2, x plus 1, but also x minus 2 quantity squared. So this time we have a different situation. For the x plus 1 part, we can still do the same thing as what we did, and that's why I used purple marker to write it, because we're still using the same method. There's nothing that we have to change. So with the same definition, we will get the residue of the function at -1 would be, again taking the limit when x approach to left, when x is approaching to -1 of the quantity x plus 1 times the original function, which again will cancel out the x plus 1 term by hand covering method. So now we just need to replace all the x by -1, giving us 3 minus 5 minus 2 on top, and we have -1 minus 2, which is -3, squared, which is 9 on the denominator. And if we simplify, we get -4 over 9. Great. So we can now quickly find out what the purple part is. However, when we talk about the x minus 2, we have two partial fractions. One of them has a linear term in the denominator, the other one has a quadratic term in the denominator. And I purposely write it in green because now it will be different from how we usually set up for the purple parts if we know the highest term is just linear. What happens if the highest term is not linear anymore? Well, first of all, the reason why I write in green is because that's not the real formal way of writing it. In fact, more formal way to write those is just leave them as how do we call it? We just leave them as the coefficients. So we can just write something like this. And again, here we already know the answer. We just throw it in. What do we get? -4 over 9. Right. Okay. Now, formally, we can write these two as the following. We have A, again, just coefficients, so you can use any letters except x, okay? And this is how most people usually denote, which is let me think about it. How do they really denote this? I believe they will denote it with this. They will put a 2 here and 2 here first to refer that the x values that we're taking is 2, which is corresponding with the denominator part. And after that, we'll then put the exponent of the denominator. In this case, the first term will just be 1 because it's linear, and then the second one will be 2 because it's quadratic. And if you want to clarify it, you can just put a comma in between or semicolon, however you want, so that you don't read it as 21 and 22. But anyway, it's just notation. Now, how do we find out these two, or these two? Let's see. Let's jump off to the conclusion first. How are we going to find out these or these? Well, here is what we are going to do. Let's say if we want to find out this one first. A2, comma 2, which I personally will write as this residue, and that is not quite correct, so let me change my notation a little bit. I'll just put a 2 down here, okay, and so that we know we're not talking about the original function up here, and then comma 2. And what does this really do? It is going to give us something like this. Yeah, I can put the limit down here. It's going to be fine. And again, since we have x minus 2 in the denominator, it also means that if we take the limit, we're trying to get x approaching to 2. So that we'll somehow be able to cancel x minus 2 terms in the denominator and get the remaining part, or the residue of it. So we have the limit when x approaching to 2. And then here, for the second term here, we actually get this. We have the original function f of x, which is the expression up here, times x minus 2. But of course, we cannot just simply get times x minus 2, because we won't be able to cancel all the copies. So to do that, in order to cancel all the copies, we just raise it to the second power. And this 2 is technically referring to this 2 right here, to remind us that how many copies we need to multiply. And this is actually kind of, this is sort of the key right here. So if we do that, we now can use the covering method again. The 2 copies in the denominator of x minus 2 will be cancelled with here, so that now on the top we have 3 times x squared, where x is 2, plus 5 times x, which is 2 again, and then minus 2 on top. And on the bottom we have x plus 1, which is 2 plus 1, or 3. Then if we simplify it, we get 12 plus 10, which is 22, minus 2, giving us 20 over 3. So this will give us the answer of the middle term. In order to find out the coefficients, or you can call it the residue, of x minus 2 squared. Now, what if we want to find out the first one? How is it going to change? This is what we're going to get. And let me write down this answer on top first, so that we won't forget. This is equal to 20 over 3. And you can check whether it's correct or not by going back to my old video and see if it matches. So now we want to get this one. What we are going to get is, now we're changing this into 1. And then this here will actually have a 2 here. So how is the whole thing going to change? This is what we need. If we look at here and here, we see that in the denominator there's only 1 copy, meaning it is only linear. So technically we don't need a 2 here in order to cancel out. However, we cannot just leave it as the linear term here either, meaning we cannot just multiply with 1 copy. Because if we go back to the definition, and again, I will explain in the next video because this is very long. If we only multiply with one copy, that residue is actually technically the sum of the two residues here. So, or it could be something related to it, but it would not just be the residue that we're trying to find. So how are we going to change it? We're going to change it with the following. We're still going to multiply with two copies. And again, why do we actually need two copies? It is because the largest power we have for x minus 2 term is actually the second power. So we'll always stick with 2 here. But since the term that we're trying to find is just a linear term in the denominator, and we multiply with 2, in order to reduce it down to the first power, one way that we can think of in calculus is, of course, taking the first derivative, right? So this is what we're going to do. We're going to take the first derivative of this product. Then, if we do that, we will now get the limit as x approaching to 2 times the derivative of this part up here. Again, using a covering method, we actually cancel the x minus 2 squared, ending up with 3x squared plus 5x minus 2 all over x plus 1. And the derivative of this fraction is, let me see, I actually don't remember. I need to write and check my notes now. This is, I believe, not so nice. Should be 3x squared plus 6x plus 7 all over x plus 1 quantity squared. And again, you can just use the quotient rule to check whether I did the derivative correct or not. And suppose it is correct, and which I believe I am. Now we can just substitute x equals 2 into the new expression, giving us 12 plus 12 plus 7, which is 31, over 2 plus 1, which is 3 squared, is 9. And this will provide us the residue, or the coefficients of the x minus 2 term. All right, let's stop right here first, and we'll go over this in the next video and try to think of the general way to express this, so that we will see how we can do the partial fraction decomposition using the residue method for any general fractional expression. Okay, I'll see you next time.